Hi, I'm Ishwar. I'm here to talk to you about the Riemann hypothesis, which is a millennium problem. If you solve it, you will be a millionaire. You will get $1 million, and it's probably one of the hardest ways to earn $1 million that I know of. So, pretty much, it all revolves around a function called the Riemann zeta function. It's an infinite sum here, and here's an example. If you take the zeta function of 2, 1 over 1 squared, plus 1 over 2 square, plus 1 over 3 square, plus 1 over 4 square, dot dot dot. And it happens to be pi squared over 6. I know, pi strikes again. So, each of these, if you keep on adding more terms, they seem to zero in on this, but on pi squared over 6, which is about 1.64. So, we have to understand it. So we have it for all numbers, most numbers. What about zeta of 1? You will end up with this infinite sum, and this actually equals infinity. This series converges. You can get any number you want. But even if you increase it by 1.001, it will still be not equal to infinity. It will still be some number. So we have a limit. But what about numbers that are not in the real plane? I'm assuming you know complex numbers, what to do with them, and derivatives. By the way, so heads up. You get 1 plus 1 over 1 plus 2 to the 2 plus I. What is this? Well, we know how to divide complex numbers, but this is actually equal to 2 to the 2 times 2 to the I. We'll go to this. What about this? This is actually like some angle which is proportional to the log of this times the number before I. And it's a rotation of the number 1, and the length will obviously be 1 over 2 squared. So when you add two complex numbers, you have to match them to tail. So if you take an infinite sum, you end up with a spiral, and the length of the spiral will still be the zeta of the real part. The length of the spiral will be pi squared over 6. So it still converges on some finite value. It zeroes in on a number. So we have it. It converges for numbers where the real part is greater than 1. But so you can graph it by letting each input point slide over to its output point, right? And have this go here, whatever. Well, if you take the grid lines and map where they go, you end up with such lovely arcs. And the beautiful thing is they all meet at right angles, just like regular grid lines do. But the thing is, they have such an abrupt stop. And it's like, isn't it just begging to be extended beyond its domain like this or something? But when you try to extend it, you can have any number of extensions. You could give a 2-year-old boy a marker and ask him to do it. But if you have a restriction on this extension, that it has to have a derivative everywhere, a complex derivative, meaning it has to be analytic. The definition of an analytic function is it has to have a derivative everywhere in the complex plane. So it walks you into one and only one solution, and you have these beautiful grid lines that make lovely arcs. Now you end up with things like this. Alright, but we still have no idea how to compute this, right? But somebody by the name of Bernhard Riemann, hence why it's called the Riemann hypothesis, developed this formula. By the way, this is called the gamma function. Gamma function of n is n minus 1 factorial. So it means if you know this, you can compute this. So since we already know it for these numbers, it kind of reflects it over the line x equals 1/2. It reflects, and you end up knowing this. Now these two parts, we know it's never 0. Well, except for some boring zeros like -2, -4 and so on, we'll ignore those. We know that all the other zeros have to be on the strip, but where on that strip is still a mystery, $1 million mystery in fact. Bernhard Riemann says, we know they must be all on the strip, But Bernhard Riemann says it has to be exactly on the middle line of the strip. and he said we know there are an infinite number of them in the strip, but one Riemann says they're all in the strip, and in fact they have a connection to prime numbers. So we actually have a lot of amazing facts about prime numbers that have been shown contingent on this hypothesis being true. It's a very important one. Bye.